Hello, let's begin by talking about fields a little bit. So part 1.1, fields. By this time you probably have seen a lot of different algebraic structures and in general structures in mathematics, like polynomials, functions, numbers of different sort, maybe matrices, maybe polytopes, maybe geometric shapes, Möbius band, and so on. These are all objects we study and we like. So among various kind of mathematical objects, there is a very special kind, which is called algebraic structures. It might happen that you have seen fields or groups, but today we will talk a lot about that, and we will see a few algebraic structures along the way of the course. So the main idea is that just sometimes we encounter in mathematics some objects which look alike. Rational numbers, real numbers are very different kind of things, but in both cases you can add them, multiply them, and for many questions they behave similarly. And there are other examples of that. So we will start by talking about fields, and fields are exactly a kind of a set endowed with two operations, addition and multiplication, which behave like they behave in the rational numbers case. So we start with a definition of what is a field. A field F is a set. So first of all, it is a set of elements of F, and we will denote the set by the same letter F. And a pair of operations. One of them is called addition, and this is a map from F times F to F. So this is Cartesian product, the set of pairs. Addition takes a pair of elements in F and sends it to a new element in F, which we call A plus B. And the second operation is called multiplication, and is denoted by a dot as usual. And it also takes a pair of elements in F and sends it to another element called A times B. Okay, so these operations and F can be absolutely anything. So of course F being real numbers or rational numbers will be the main example, but actually later on I will introduce examples when the set F is finite and addition and multiplication look very differently from usual addition and multiplication. So these maps should be not arbitrary, of course, but they should satisfy a few properties. So there are a few groups of properties, three groups of properties, and let me try to list all of them. I will hopefully be able to do it. So first four properties are properties of addition. The first one is called associativity. For every three elements A, B, C, and F, A plus B plus C equals to A plus B plus C. So the idea is that this mimics the usual properties of addition and multiplication, which hold in real numbers or rational numbers case. So the second property is also very natural. For every elements A, B, and F, A plus B equals to B plus A, commutativity. So the third one says that there exists a special element called 0 inside F. It is just a notation, has nothing to do with usual 0 in real number, or at least may have nothing to do. Such that for every element A in the field, A plus 0 equal to A. And the final property of addition is that for every element A in the field, there exists another element, which we will call minus A, also inside F, which satisfies the natural property that A plus minus A is equal to 0, which was just introduced before. Okay, so these are properties of addition. Actually, a set with one operation in this structure is called a abelian group. It's also very interesting, but we will not talk about it in this course. So then there are a few properties of multiplication, which are the same basically. So firstly, when you multiply three elements, again, you can put brackets as you like. A second property is the same thing with commutativity. Third property, third property is that there exists a special element called 1 inside F such that A times 1 equal to A for every element A. And final property of multiplication is that for every element A not equal to 0, there exists an element 1 over A. It's just a notation inside F such that A times 1 over A equals to 1. So here addition and multiplication are not related. So all properties are either properties of addition or of multiplication. So the last property is that for every elements A, B, C, and F, A times B plus C equals AB plus AC, called distributivity. It relates these two properties. So this is everything, and any set with two operations satisfying all these properties will be called a field. There are tons of important fields in mathematics. So I will give you several examples, but there are many more. So let me start with the most naive example. So the first naive example is that rational numbers and real numbers are fields. So you take real numbers or rational numbers with usual operations, with usual notion of 0 and 1, and these are fields satisfying all these usual axioms. So second is a non-example, so Z is not a field. Again, with usual operations. Why? So all properties of addition are the same, and distributivity holds, multiplication is associative, it is commutative, there exists one, but this property 2D does not hold. Because, for instance, 1 over 2 is not integer anymore. So that's why Z is not a field. Okay, so now let's make a few examples of fields which are more interesting. Okay, so third example is one of the most important examples of fields which are not rational numbers, not real numbers, complex numbers. So complex numbers are very important. They will appear in this course a lot of times. And so let me start by saying a few things about complex numbers and actually proving their existence. I don't know, probably most of you have seen this construction, but just for clarity, let me do it for completeness, maybe. Okay, so everybody knows probably what complex numbers are supposed to do. So, okay, so square root of -1, usually denoted by I, is a complex number. And then maybe you have seen that actually a typical complex number looks like a pair A plus BI, where A and B are real numbers. And also you might have seen the rules for their addition and multiplication. So A plus BI plus C plus DI equals A plus C plus B plus DI. And similarly, A plus BI times C plus DI equals AC minus BD plus BC plus AD times I. So how to remember these rules? I just operate with them as usual numbers, using usual properties of addition and multiplication, and remember that I squared equals to -1. This is why this fun minus sign appears here. Okay, so this is of course not a definition, it's just a way to operate with them. But let me actually use it to define complex numbers. So it's kind of obvious that a complex number is a pair of real numbers, a and b. So let's just define. So this all was just a remark. So let's start with a definition. So a set of complex numbers C is just R times R. So a typical example of a complex number here, Z, is just a pair of real numbers A and B. So this pair will eventually correspond to number A plus BI, but yet we don't know that. Okay, so then we introduce a definition, so we define addition. So according to our definition of a field, we need a map from C to times C into C. So this map should take a pair AB and another pair CD, and then we just put by definition A plus C, B plus D. So we definitely can make this definition because, okay, so this map is well defined. Then we define multiplication, also from C times C to C, taking a pair AB times CD to B, and then, of course, we can do something like AC comma BD, but this will be actually not a field. So what we do, we define it forcefully by this strange rule. So we take a pair AC minus BD, comma, BC plus AD. And this is how we multiply complex numbers. Okay, and then we can prove a proposition. C is a field. So to do that, we need to actually check lots of properties. And some of them become quite non-trivial. So, and proof is an exercise. But just to sketch that, so properties of addition. Associativity is obvious because it will hold in each coordinate separately. And similarly, commutativity is obvious. So 0 complex number should be a pair which has a property that if you add it to any other pair, you get this pair back. And so clearly it should be 0, 0 thing. So what about 1? So I claim that 1 should be just a pair 1, comma 0. And indeed, if we use this rule to multiply, a comma b times 1, comma 0 will equal to AC minus BD, which is A, comma, A0, BC minus BC plus AD, BC plus AD, B, A, comma B, right? Okay. So 0 is this one, 1 is this one, and for instance, to check associativity, we need to take 3 pairs and multiply them in 2 different ways, and we will get a long identity, which actually we will need to check that it is true, and it will be true. Okay, so what about square root of minus 1? So it is easy to see that 0, comma 1 square equals to minus 1. So just using this rule. And we will just define E, we put it by definition to be equal to 0, comma 1 pair. Okay. Another observation is that a pair A, comma B actually equals to A, comma 0 plus B, comma 0 times 0, comma 1. Again, this is just a simple bracket opening. And then we define A, comma B, A, comma 0. We denote it by A. It is simple to check that the way we add and multiply pairs A, comma 0 is exactly the same way in which we add and multiply numbers A. So we can just identify such pairs with A. Formally speaking, here we need to talk about isomorphisms of 2 different fields, but we will skip that. So let's just define it by A, and then A, comma B will be just a pair from here we see that it is just a plus bi. Okay, so this is the main idea of construction of complex numbers. And to check all the axioms, maybe the most interesting one is existence of an inverse. And so what is the inverse of a plus bi? So 1 over a plus bi. The usual trick is to divide and multiply on the conjugate, and we get a minus bi divided by s squared plus b squared, which is a over a squared plus b squared minus b a squared plus b squared I. So in this way we can divide complex numbers. So this is it, and then one can develop the whole theory of complex numbers, identify them with the points of a plane, vectors inside R2, and so on and so forth. So what is interesting about that, it does not question their existence. So we have just give a definition and checked all its usual properties. And check that it is a field. Okay, let's make a break here.